So hi everyone, just to give you an idea of my background, I'm a software engineer and a technical project manager at the University of Queensland. But I've been part of the Maker community here in Brisbane for quite some time. And I will admit up front that although I do occasionally still dabble in Python, I'm actually more of a Node.js developer these days. Please don't hate me. So do please forgive me if some of my code looks a little bit weird, or if there's a stray semicolon or bracket in there somewhere, because habits are hard to break. But what I'm going to talk about today applies regardless of language. So for the past 15 years, I guess, I've been involved in teaching introductory programming. First as a tutor at the University of Queensland, and then as a technical trainer at a research organisation, and more recently through involvement with community groups, so things like GovHack and the Open Knowledge Foundation. And one thing that I've discovered, I guess, from teaching people how to code now is that I was lucky to be born at the right time. So I learned how to code at school in the 1980s, and I've basically grown up and matured as a developer as the industry and as the internet kind of grew and matured as well. So it's been pretty easy for me to keep track of new developments and to learn new things and to build on my knowledge as new things come out. But for people who are learning how to code from scratch now, the situation is really quite different for them. And learning how to code can be pretty exhausting. There's almost too much information available. People are inundated with different choices in terms of what language, what framework, what library, best practices, opinions. It's difficult to know where to start with learning to code. And even as a seasoned developer, or perhaps particularly as a seasoned developer, I'm quite anxious about helping people with learning to code, because what if I'm steering them in the wrong direction? The choices that they make as they're starting could be things that they develop across their entire career. So what editor should they use, tabs or spaces, just even simple things like that. So what I want to do is basically take a step back from that, from the serious business of teaching how to code, and to talk a little bit more about just the fun of learning how to code. So in the last couple of years, I've expanded from just teaching introductory coding to teaching introduction to electronics and introduction to Arduino. And eventually those two things kind of overlapped. And so now I'm actually using Arduino-based robots to teach coding. So this is a picture from International NodeBots Day last weekend, which was at the Edge. This is in Brisbane. And we had about 45 people turn up on a Saturday afternoon to learn how to code using robots. And this was an event that actually happened all across the world. It wasn't just here in Brisbane. There was a similar, actually larger event in Melbourne and Sydney, and in fact distributed in cities across the world. We basically passed the torch, and it went to Cape Town, it went to America, it went to Europe. So there were literally hundreds of people learning how to code, many of them for the first time, with robots last weekend, which is really cool. And the feedback that we've had from participants has been pretty awesome. So this is a tweet. Basically, his 10-year-old son said it was the most fun 6 hours of his life. That's pretty high praise. So one of the other things that we had with our robot workshops that we've been running is that it's been a very diverse audience. So usually if you run an introduction to programming course, you get not a lot of women, not a lot of diversity happening, but you can see from the pictures and definitely from the workshops we've had, everybody loves to build robots. So what I want to talk about today is just kind of how I think learning to code is improved with robots. And these are just a couple of examples of the sorts of robots that people built. These are from some workshops a few months ago that I facilitated at the Edge. And you can see they're not complicated robots. They're pretty much held together with cable tie and sticky tape and pipe cleaners and things. It's not about building a fantastic robot, it's about learning. So building robots like this is a lot of fun, but I've realized that it's not only great fun, but it's also an ideal space for teaching coding. So please indulge me for a few minutes while I kind of talk about why I think robots are a great way to learn to code. And when I'm talking about robots, I'm not just meaning robots like, you know, these kind of little things that we built, but I'm also talking about physical computing. So the fact that you've got hardware, you've got sensors, you've got actuators, so interactive systems that sense and respond to the physical world. So even just blinking an LED, that's fine. It doesn't have to be a fully fledged robot. But robots themselves are basically autonomous systems that sense and respond to the physical world, usually to perform some sort of task. So they're kind of a subclass of physical computing, if you like. But why do I think robots are the way to go? So before we step through some actual code to show how to do some physical computing with Python, let me just reminisce a little bit. So when I learned how to code, I learned using a language called Logo. And this was developed in the late 1960s. It was a language that was specifically designed for teaching coding to kids in particular. And one of the most memorable parts of Logo is the turtle, which you can see on the screen here. It's basically, you can use commands like forward, left, right, and back to tell that turtle where to move along the screen, and it drags a pen behind it and draws a path. Now, I was really surprised to see that in the Intro to Python course that was running at the Edge yesterday, turtle graphics were part of that course. So even though this language was developed a long time ago, and probably not very many people are using Logo itself, turtle graphics has kind of survived beyond Logo. And it's still a useful way of teaching programming concepts. Now, Logo was developed by a group of people. One of them was called Seymour Papert, and he's a computer scientist and an educator. Now, he came up with this idea of, well, among other learning theories, of body syntonic reasoning. So this is the way that turtle graphics works. Basically, the idea is that we have a very good understanding of our own bodies, and we can use that to reason about other situations. So as a student, when I was learning how to code with Logo, I could imagine myself as the turtle on the screen, and I could imagine and predict what it would do if I told that turtle to move forward a certain number of steps or to turn left a certain number of degrees. So I would argue that teaching with physical robots like this buys into this same model, this same learning theory, and in fact even more so, because unlike the Logo turtle, which is a bunch of pixels on a screen, a robot is a physical device that exists in the real world, the same as us. So it's even less of a leap to imagine how this robot will move in response to commands. One of the other learning theories that Seymour Papert came up with was called constructionism. Now, this is also closely related to the physicality of robots. So it's very, if you are familiar with the work of Jean Piaget, who is a very influential developmental psychologist, it's based on constructivism, which is closely related but not exactly the same, and experience-based learning. So the idea with constructivism is that students construct mental models of things around them based on their own experiences. But Papert actually extended that idea by saying that learning is most effective when we not only create a mental model, but we actually create something tangible that is a physical object in the real world. He wrote a book about this. It was published in 1980, again quite a while ago, called Mindstorms, Children, Computers, and Powerful Ideas. And incidentally, this is the inspiration for the naming of the Lego Mindstorms kits. This is why they were called Mindstorms. So it's a powerful idea, teaching coding through physical objects like computing. So we're certainly in good company, because Mindstorms kits are still used to this day in schools. So the learning theory kind of supports using robots to teach coding. But what about my own personal experiences? Because I'm not an expert in learning theories, and some of these theories that I've presented here are really quite old and probably not all that trendy anymore. There's probably new theories out there. But my own experience supports the fact that learning to code with robots is a useful thing to do. So one of the things that's really great with Python and with JavaScript is that it's an interpreted language. So you get that immediate feedback. You can make a change to the code, you can run it through a REPL, a read, eval, print loop, and your robot will immediately respond to that code. So it really supports the idea of exploratory programming, where you don't have a kind of an idea of what you want to do, you don't have a spec, requirement spec. All you're doing is basically exploring a particular space, a particular API, a particular framework, and working out what's possible and how you can use it. So what I do often in the workshops that I'm involved with is set some challenges for people. So you give them a few basic primitives to work with. So you tell them, for example, how to make a servo move, controls the wheels, and then give them a challenge to make a robot move around a certain obstacle path, or to do something, go forward a certain amount and turn left, much like a turtle. One of the other things about, that I've noticed in teaching robotics and teaching programming with robotics is that it makes it quite easy to teach some of the things that are difficult with non-physical examples. So one of the most important things to learn about when you're learning to code is abstraction. And object-oriented programming languages, objects, that's a really important abstraction, a really important concept to understand. But a lot of introductory programming courses leave that until later. They don't kind of come up front with objects. You learn basically declarative programming, procedural programming first, and then you kind of add to that your understanding of how to construct objects and how to sort of compose, break a complex problem down into smaller pieces and to decompose it. And I think that this is a mistake to leave it as a secondary thing. I think we should be teaching people about abstraction and about how to understand the kind of the paradigm of the language right from the beginning. But it's always something that I found challenging to teach. So object-oriented programming as a concept is a pretty difficult one for people to get their head around, and it takes some time usually. When you're running a robot workshop that might only last for a few hours, you don't really have the luxury of time. But surprisingly, I found that it hasn't been an issue at all. And I think this is because there's almost a one-to-one correspondence between objects in the physical world and their representations in code. So it's quite easy and natural to explain to someone how a robot is an object that has state and behavior, and it's composed of smaller parts like sensors and servos that also have their own state and behavior, and that these can be the details of these can be hidden away from the robot, so encapsulation, you can teach that. There are also a number of different components that are similar to each other but not quite the same. For example, the servos, which are the motors that are used to drive the wheels, are continuous rotation servos. They go from 0 to 360, full circle, whereas smaller hobby servos, like the one that is on the head of the robot, only goes 180 degrees. So these are very similar components. We can teach subclassing, for example, through understanding that there are things that are similar but a little bit different in the same class of objects. So let's get to actually looking at some code and looking at how I would teach physical computing with Python. But first, one of the things that I find when I'm trying to teach people coding, I feel a bit like this. So I'm kind of like, do you want to write some code? And people are kind of like, yeah, go away, Anna. I get really excited about it because I know how awesome it is. But when it comes to robots, I don't have to convince people. Robots are just awesome in their own right. So people are almost learning to code despite themselves. And I can sneak in a lot of theory and a lot of kind of stuff that might not be so exciting if it wasn't in the context of robotics. But let's step through how I design my robots. So robots, there's a lot of different types of robots out there, obviously, and I'm really talking about these kind of, do-it-yourself robots. Now, all the robots that I work with are built on top of the Arduino platform. It's an open source hardware platform, a microcontroller, and they all use pretty much off-the-shelf hardware. So servos and buttons and LEDs and that sort of thing. Now with the robots that I developed, basically there's a bunch of components that are sensors, that are inputs for the robot. So these are things like the ultrasonic sensor that basically measures distance to an obstacle. There's the Arduino, which is the brain, the microcontroller. And then there are the outputs, the actuators. But in addition to this, there's also the chassis, which in my case is actually some recycled micro-titration plates that are basically just holding all the bits together. And then there's the power, it's just some AA batteries. Now when it comes to the sensors, every workshop that I run might have different sensors. There's just so many out there to choose from. There are two kinds of types of sensors that usually talked about in robotics, exteroceptive and proprioceptive. Basically, exteroceptive are the sensors that sense the outside world, so the outside state. So most of these are external sensors. And the proprioceptive sensors are the ones that sense the internal state of the robot. So this might be something that detects how many rotations the motor has had, something like that. So there are, sensors that measure environmental conditions, like temperature sensors are really easy to work with, humidity, smoke detectors. Magnetic sensors, they're called Hall effect sensors. They're really easy to come by because they're used in 3D printers quite often, so they're quite cheap and readily available. Light sensors, like a photoresistor is about 5 cents. So you can throw a whole bunch of them on your robot and work with sensors very easily. And then obviously there's sound and motion and also things like buttons to detect when a user presses a button, or even, in this case, I've got buttons on the bumper bar, so if the robot runs into something, it triggers those buttons and it knows, well, I can write some code to make it back off. In terms of actuators, so the sensors are the inputs, actuators are the outputs. So there's light and displays, so LEDs being the most obvious one, LCDs as well, OLED displays. There are sound modules, so you can get like a piezo buzzer that just makes a beeping noise. Obviously with robots, motion is really important type of an output, so you've got lots of different types of motors that you might use. I tend to use servos more than anything else because they're so easy to work with. So I use continuous rotation servos for the wheels, and I use smaller servos to move arms or heads or so forth. And then there's things like power. You can attach a relay and basically control any device through a relay. So how do we interface with this hardware through Python? Well, conveniently, there is a library called PyFormata. And yesterday, we ran an Intro to Electronics in Python workshop at the Edge, and I can see a few people who were there in the audience. I'll admit that's my first time ever running a workshop using Python for this stuff, so we're kind of all learning as we went along. But when I use Node.js, I actually use the same protocol as PyFormata. The Formata protocol is designed to be used with lots of different languages, and in fact there are bindings for Ruby and other languages if you wanted to use those other languages. But PyFormata, you get it from this GitHub repository. Basically, you run a program on your computer. We were using Raspberry Pis, and you then communicate with the Arduino over a serial connection. So USB being the most obvious one, but you can also communicate over Bluetooth. That's just serial. And I've also had some luck with using little Wi-Fi modules and SOCAT and being able to talk to the robots that way. If you want to play with PyFormata at home, you can basically install it using pip. So pip install PyFormata will get the library for you. Be warned though, it does only seem to work with Python 2.x. Didn't work with 3 for some reason, even though it said it should. Just couldn't get it working. So Hello World for robots is basically blinking an LED. So let's step through how we would do that using PyFormata. The first thing we'd need to do is actually attach the LED to the Arduino. And here I'm using an Arduino Nano, which is, you probably can't see this from where you are, but it's a very, very small Arduino that I've got on this robot here. It's a lot smaller than what you might have seen as an Arduino Uno, which is basically the same pin layout, just in a larger form factor. But Nanos are great for robots because they're small and light. So basically, you'd connect that LED up to the robot, and the way that Arduinos work is they have a number of I/O pins. Some of them are digital, some of them are analog, An LED, so if we just want to blink it on and off, that's a digital I/O. So we connect it to one of the digital pins. We connect positive to, say, pin 13 on the Arduino, and then we'd connect the ground pin to the other lead. Then we create a Python program, and in fact, you can use whatever environment you want to use. You could use the console directly. We were using IPython Notebook yesterday, but you can, of course, just create your code in a Python program file like you normally would using your favorite text editor. You need to import PyFormata at the start of your program. And then you need to create an object to talk to the Arduino itself, so a board object. With PyFormata, you need to explicitly tell it which port your Arduino is connected to. That's one of the things that Node.js does, is it automatically detects it. So if anyone, incidentally, is looking for an open source kind of a project that they want to work with, there's a lot of work that can be done with PyFormata. So come and talk to me afterwards if you're interested in writing some stuff to improve that library. But basically, you give it a port, which is just the device that your Arduino is connected to. And then we can control that LED by talking to that pin. So you'll notice that this is really kind of low-level code. We are actually saying, give me a digital pin. We're giving it a number, that's pin 13 on the Arduino, and then we're writing to that pin either a 1 or a 0, so setting it to be high or low. This is in binary directly. And this is one of the things that I really like about teaching with robots, is that you really do start right at the basics and kind of build up from there. So it's kind of a full stack learning experience, if you like, which is maybe the opposite to the way that it's normally taught. Anyway, so we can turn our LED on and off. We can also delay that behavior, so we can cause the LED to blink. There's a pass time function built into PyFormata that makes that really easy. So we can just do this. And so the code to basically blink our LED on and off, let's say we just wanted to do it infinitely, we could do something like this. Just put it in a while loop and just turn that LED on and off. Now, you'll notice that this, is, as I said, is really low level, and probably you would want to do things like write some classes to make this a little bit nicer to work with. So, for example, you create an LED class that lets you just instantiate an LED object, telling it which pin to connect to, and then you might have something like on and off. And there are lots of different things that you can do with LEDs. You might want to pulse it, you might want to do some patterns. You could build that into the class. And the Node.js libraries do actually have all this stuff in there already. I won't keep going on about Node.js, but yeah, this is definitely an area of improvement. So please do come and talk to me if you're interested in writing some classes like this. Now, one of the things that we use to talk to hardware is pulse width modulation. So this is basically where you've got a digital pin and you don't just want to have an on or an off. You want to sort of simulate a continuous signal. And this is really important if you want to do things like fade an LED, or if you want to talk to servos. Basically, they're digital actuators and they need PWM to be able to drive them. So basically, a square wave is sent to simulate that voltage between 0 and 5 volts. But it's only enabled for some pins on the Arduino. It's 3, 5, 6, 9, 10, and 11 on a standard Arduino, for example. So knowing that, we can then talk to the pins using PWM instead of just digital output to do things like blend colors in an RGB LED. So an RGB LED is much like a standard LED, except that it's got 3 colors in one. So we'd connect our RGB like this, some resistors to make sure we don't blow the LED up. And then instead of setting our digital pin to output mode like we did in this example, we'd set it to use P. So where we've got board get pin, D:10:P, for example, that's basically a specification of how the Arduino interfaces with that device. So it's a digital pin, it's pin number 10, and it's using PWM rather than just digital input or output. And so we could do something like create random colors by blending different values of red, green, and blue. Movement is also really simple with PWM. Basically, you connect a servo. A servo has 3 wires, 5 volts, ground, and a signal. and we use the same technique. We can use PWM, but actually PyFormata has a servo type of connection built in as well that makes it a little bit easier to work with them. So we can do something like this. We can write a function, for example, that uses a servo write function, and we set a value in degrees to move that servo to a particular position. Working with sensors, so inputs this time, is also pretty easy. So if we were to connect something like a photoresistor, we'd wire it up like this, and then we'd read from that analog sensor by basically using an input mode instead of an output mode on that pin. And one of the things that's important to do with PyFormata is to set up this iterator just so you don't kind of flood the serial connection with readings. So that's just something that you learn from experience. You can also read digital input. So while a photoresistor is kind of a continuous range of values representing the ambient light, a button, for example, is just either pressed or it's not pressed. So we can do the same thing with digital input and a button. I've put these learning resources in the slides because I will share them later. So if you want to go and play with PyFormata or learn some more about electricity, there's some examples here. Arduino Playground. I've written some examples from the workshop yesterday, which are on a GIST. And just in case you're interested, there is the Node.js version up there. But let's just talk about the future for a couple of minutes to conclude. So, because when we're talking about teaching, we're talking about the future. We're talking about transferring our skills, our knowledge, our hopes, our aspirations, our enthusiasm to a new generation of coders. And when it comes to thinking about the future, robots are right up there with hoverboards and flying cars. They evoke the future. Now, since the 1920s, when the term robot was coined, and it actually means slave in Slavic, we've been promised this kind of future utopia where we'd have robots around us as our personal slaves. And while I do have a Roomba and I like not having to vacuum, that's not the future I'm excited about for robots. Actually, I think something that's far more important in this space is the Internet of Things. So this is a quote from Cisco. It says, basically, during 2008, the number of things connected to the internet exceeded the number of people on Earth. So robots are already among us when you think of these devices as being autonomous devices that sense and respond to the physical world. But if we think about the way that the internet in general and the web has developed, we've seen that originally it was developed in a kind of an academic setting by nerds, and I'm proud to be a nerd. And then it was embraced by corporations for good or for evil. But because it was originally built on standards and open source and open hardware, open technologies, we still are able to use that platform to pretty much do whatever we want, at least for now. But when we think about the future of the Internet of Things, we can talk about the possible futures, we can talk about the plausible futures, we can talk about the probable futures, but I think it's really important that we think about the preferable future. So something that really worries me at the moment about the way that the Internet of Things is developing is kind of this trend for it to be driven by large corporations, the Googles, the Facebooks, the Ciscos, the IBMs of the world. Now, Alan Kay, who was actually a colleague of Sima Papert, said that the best way to predict the future is to invent it. And we need more people on our team, the open source, open Internet of Things team. So while platforms like Lego Mindstorms, for example, are teaching people how to do coding in the context of robotics, they are closed and proprietary platforms. And we should be working towards making open platforms like Arduino with robots just as easy to work with and just as accessible. One of the things that Papert said was, should the computer program the kid, or should the kid program the computer? And with consumer devices like phones and so forth that are probably a lot of people's first experience of computing now, they're definitely programming people to be passive consumers. Sorry. And this is why maker culture is so important to me. So I was really heartened to hear James Curran talk this morning about Python being taught in schools, and that every Australian child could be learning Python, because Python is an amazing language for learning, and it is actually, I think, better than JavaScript for teaching. So what I want you to take away from this talk, and I'm wrapping up now, is that while building robots is lots of fun, I think it's really, really important as well. So if you're a teacher or a mentor, be inclusive. Teaching is not your chance to show off. It's basically your chance to teach the joy of making to somebody else. So tell them that it's okay to pick under the covers, it's okay to hack, to break things. You're helping people to discover how to think like a programmer, not what to think. And if you're a student, don't sweat the details. And by that I mean, don't worry about the language or the framework or the trendy thing that you're learning. Just learn, the basics of coding. What matters is that you don't lose the sense of wonder that you first experienced when you made that LED blink the first time or that turtle move across the screen, because the best way to get better at coding is to love it and to just keep doing it. And everything else is just details. So get excited and break things.
Thank you very much, Anna. Put your hands together for it.